Welcome. In this video, I'll be covering GraphLab, which is a programming framework that is dedicated to processing of graphs. So let's talk about graphs. Graphs are quite useful to represent various types of data. And let's take a look at a few examples of data that can be represented as graphs. The first is the social network. In a social network, each vertex is representing a person or an entity, and each edge can represent a friend relationship, or maybe in the case of Twitter, a followers relationship. Then we have road networks. In a road network, every vertex is an intersection, and an edge is a road that connects two intersections. And then we have the web graph, where every vertex is a web page and each edge is a link from one page to another. Now let's look at some of the operations that can be performed on graphs. So first we have the min-max average degree of the graph, which is a computation of the number of edges that are there on each vertex. There's the diameter of the graph, which is the maximum distance between two nodes in a graph. And then, of course, there's the min-cut-max flow computations, which allow you to find optimal paths in a given graph. Then there are traversals, which is an order in which you visit the various vertices on a graph, and this is useful for many types of applications. An important canonical example of an operation on a graph is PageRank. Now, PageRank can be used to find the relative importance of a particular page given a particular term or word. And PageRank is one of the bases for web search engines. The problem of PageRank is also in many cases quite large scale, because you want to compute the rank of a particular page from a set of millions or billions of web pages. In fact, one of the largest publicly available web graphs consists of about 1.7 billion web pages and 64 billion links. And this is believed to be much smaller than the actual production data used by companies that run massive search engines such as Google, Yahoo, and Microsoft. And then there are other machine learning and data mining algorithms that can be represented as operations on graphs. So one of the early graph computation frameworks that emerged in the last decade or so is Pregel. Pregel is Google's framework for graph computation. And in Pregel, every vertex is assigned an ID. During the course of the computation, a vertex will be assigned values at different intervals. So essentially, you are writing a program that is designed to run on a vertex, and depending on the graph structure, values can be assigned to edges and passed on to other vertices. So the way in which Pregel executes the computation on these vertices is in something called the bulk synchronous parallel style execution. So what happens is it schedules the computation to happen on every vertex as super steps. And what happens in each super step is each vertex will perform its computation and then wait for every other vertex to complete its computation, and thereby you have a barrier. One successful computation of all of the vertices in a graph is known as a superstep or iteration. And after the barrier, then messages are passed between all vertices to start the next iteration or superstep, and so on. Now, there are problems, obviously, with Pregel and BSP, some of which are quite apparent right now. So this lockstep execution works pretty fine if your computation is fairly balanced, in the sense that every vertex has roughly equal amount of work to do and they kind of finish in the same time. Remember the social network graph that we talked about a few slides earlier? Well, this is an example of a natural graph or a social graph in which certain nodes have more connections than others. And in many cases, such as the Twitter web graph, it's quite high. So there are certain celebrities that have millions of followers, and hence they have, millions of edges. Whereas there are, millions of users that have only a handful of followers. So this is a highly skewed graph, because a majority of the vertices have very low degree, but there's a very small number of vertices that have a very, very high degree. Now, if you were to execute a graph computation using the lockstep form for these kind of graphs, what would happen is the vertices that have the most number of edges will typically end up having the most amount of computation and will always be the bottleneck at each iteration. So the execution of each iteration is dependent on the last vertex to finish executing. And what happens then is every other vertex will end up simply sitting and waiting most of the time. And this ends up being in a situation where you're not fully exploiting the parallelism, especially for some types of problems in which you don't necessarily need strict lockstep execution, where you might be able to do some computation for certain vertices across iterations. So that's kind of the motivation for GraphLab. GraphLab is a graph parallel execution framework which has specific optimizations for large natural graphs. And there are multiple versions of GraphLab. The very first version was 1.0, which was kind of GraphLab for multi-core machines. In 2.0, there was the release of PowerGraph, which was optimized for natural graphs and scaled to distributed nodes. Currently, there's a new version called GraphLab Create, but this is a commercial version that has been released by a startup company associated with the GraphLab project. So in this video, we'll cover the last open source version of GraphLab, which is PowerGraph. So let's talk about some of the specific optimizations that GraphLab does in order to speed up graph-based computation. The first is the partitioning of graphs and specific optimizations to partition natural graphs. Now, in the partitioning stage, a large graph has to be divided among multiple machines. Now, one of the ways you could do this is using the edge cut metric. In this idea, individual vertices are assigned to individual machines. So if you have 4 vertices, in this case, A, B, C, and D, I give, using a random allotment, I give A, B, and C to machine 1 and vertex D to machine 2. Now, there are edges that may span machines. For example, there will be edges from A to D, which need to be somehow represented in this matrix. So what happens is we have a secondary class of vertices that we will keep on each machine known as ghost vertices that will keep track of vertices that are on other machines other than the one in question. So for example, machine 1 has a ghost vertex D, which represents the vertex that is on machine 2. So it will have information regarding, okay, exactly is vertex D and how do I contact it? Similarly, machine 2 has ghost vertices A, B, and C, which represent the vertices that are available on machine 1. Now, the edge cut metric is a simple representation of partitioning of a graph across multiple machines. It is simple in the sense, it is usually known upfront how many vertices a graph has, and you could just randomly split the vertices between multiple machines, keeping ghost vertices to keep track of remote vertices. However, this is not necessarily a great partitioning strategy in case you have social network style graphs which are highly unbalanced and have certain vertices which have a large number of edges. Because what happens in that situation is, say, in this example, vertex D is the one that has a very high degree as compared to A, B, and C. Then the machine that is executing vertex D will have to process more information because there are a lot more edges incident to vertex D. So this will also cause an imbalance in the computation. Now, the other strategy, instead of cutting the edges, is to split the vertices. Now, in this example, we have the assignment of the same vertices A, B, C, and D, but instead of splitting the edges, I'm simply splitting the vertex D to exist in 2 different machines. Now, machine 1 will have the main vertex D available, but I also keep a mirror of the vertex in machine 2. And in machine 1, there will be the incident edges of A and B, whereas machine 2 will have another vertex incident to it, which is C. So the mirror also contains information saying that I'm not the complete representation of this vertex. There is a copy of my vertex on machine 2. So the mirror vertices can be used to keep track of vertices across different machines, and this was shown by the GraphLab team to perform better on natural graphs. Apart from the partitioning of natural graphs, there is the question of execution engines and how do you schedule vertices to run on multiple machines. One of the first engines and the simplest engine that you can think of is an exact copy of the BSP based engine in Pregel, which is a synchronous engine. In this example, all vertices will always be on the same iteration and will execute in lockstep using barriers. And there are certain types of problems that require synchronous execution. If two vertices were to execute in different iterations, for certain applications, the messages that they may exchange may cause, divergence or an incorrect answer. So there are certain execution engines in which they require an absolute synchronous engine. Then there is the idea of asynchronous, where you do not place a barrier and you simply execute the vertex programs in any order, basically. So you're not keeping any barriers, you're allowing the vertices to execute simultaneously without stopping for any other vertex. And there are certain problems in which asynchronous is fine, because maybe the rate of divergence isn't affected as much, even though some vertices may receive stale information from previous iterations. And finally, there is the asynchronous serializable execution engine, which gives some control to the order in which the asynchronous execution engine executes on certain vertices. And this is achieved by locking some vertices. So for example, when a vertex enters an iteration, it will get a lock on all of its neighboring edges and vertices just to make sure that they don't execute while this particular vertex is executing. So let's look at how you would write a GraphLab program. Similar to MapReduce, where you have two main functions that you have to write that will execute on all of the data, which is map and reduce, a GraphLab program has an abstraction known as the gather, apply, and scatter execution paradigm. So in the gather phase, a vertex will retrieve all of the messages from all of its neighboring vertices. And in the apply phase, it will compute some sort of aggregated value for all of the messages that it receives. And finally, in the scatter phase, it will send that information to all other vertices. As an example of how this paradigm works, let's look at PageRank. Now, this is the formula that we will use to calculate the rank of a particular vertex. It's nothing but a constant factor, 0.15, times the sum of the rank of all of the neighbors of a vertex, which is Rj, multiplied by some weight for those ranks, which is denoted by Wji. So in the first phase, we gather information about the neighborhood. So what happens is we initialize a variable called total, and for every neighbor that is a neighbor of vertex I, we compute the total to be the rank of those vertices times the weight of the edge that connects this vertex to its neighbors. So we compute a new total. And in the apply phase, we update the vertex. So now that we've computed a total from all of the neighbors of a particular vertex, we add a certain value to it, some constant value that is 0.1 or 0.15. And then what happens is we have to signal the neighbors and modify the edge data in the scatter phase. So we compare the old rank of a particular vertex and the new rank of a particular vertex and see if they have changed within a certain threshold. Then this is what we call convergence. So if R of I has changed between iterations significantly enough, then what we do is for every neighbor that exists for that particular vertex, we have to scatter a message saying that, hey, this rank has changed, so you also probably need to recompute your ranks. And so this completes one iteration of the gather, apply, and scatter programs on a vertex. And this will continue running until all ranks have been converged within a certain threshold. Now, setting this threshold is also quite important, because if you set a very low threshold, sometimes this algorithm might not converge. So there's a little bit of an art in how you set this up to make sure that the program actually finishes execution.